Hello everyone and welcome to this video where we discuss things mathematics and physics on the board. Now this particular video is actually a follow-up from a video, so it's part of a video series of 3 videos where we actually try to derive what would be the Hodge dual of let's say one form, 2 forms, or if you prefer 1 vector or 2 vectors and 3 vectors in R cross R3. Okay. So that's, of course, is going to have some implications for special relativity and how we write forms in special relativity and so on and so forth, and their corresponding duals. So just to put a bit of perspective, so I'm going to put as well like a video here or somewhere where you can have a look at how we did with 1 forms or 1 vectors to calculate the duals, but otherwise today what we are going to look at is basically 2 forms. Right, okay, so first of all, let's summarize a bit the ideas. This is the same as what we did in the first video. So I just summarized that if you have 2 sets of k vectors or k forms, basically with a corresponding basis, then you basically you've got that, and this is defined in R4. Okay, so you've got a basis of 4 vectors in there, and then you've got an inner product with a signature here that I've chosen to be plus, minus, minus, minus. Okay, I personally prefer this one because I don't like to have to deal with ds squared that are negative. Now you've got also a bilinear map, which is a bit more complicated looking, whereby if you take the f of some wedge product of these k vectors, and then in the first kind of slot, and then the wedge product of k vectors as well of another set, then this is going to be equal to the determinant of the matrix that is made out of the inner product of the different pairs you can make between these different vectors here. And so after that, you actually define the Hodge dual of beta as star beta, such that it satisfies this particular relationship, where here this one is a so-called canonical volume form, or corresponding to the canonical basis E0, E1, E2, E3 in this particular space. Okay, so basically that's it. And to start, so now we are looking at the case k equal 2, and what that means is that alpha is going to have this particular expansion in terms of 2 forms or 2 vectors, and here beta is going to have essentially the same kind of expansion. Now, just in case you're not sure, again, I use the same strategy as last time. I actually start with the first pair as being, let's say, 0, 1, and then the next pair I simply shift rightward. So there's going to be 1, 2, and then 2, 3, and then 3, 0. And I basically have done the totality of the possible pairs, and where only one order is possible. And I do the same here as well. So next, I'm going to say that correspondingly star beta is also therefore a 2 form, and so it's going to have the components beta tilde 0, 1, E0, E1. So it's quite easy actually, because I just need to reproduce the same thing, but with tilde, that's the name I give to the components of star B, just because otherwise it's a bit too cumbersome. And then E1, E2, plus beta tilde 2, 3, E2, E3, and then beta tilde 3, 0, E3, E0. Okay, so then what I need to look at is alpha. So alpha wedge star beta, and so that's going to be interesting, because I need to look at all the and the only way usually I can actually get a wedge product between this and some of the guys here in such a way that I actually get the volume form, so this canonical form here. So there is usually only one way to do it, otherwise we are going to repeat things. So here, for example, let's say I've got alpha 0, 1, E0, E1. So the two that are missing are E2 and E3. So I just need to find E2 and E3 here, and basically that's the only one that is going to be non-zero. So alpha 0, 1, and then beta tilde 2, 3, and then I've got E0, E1, and then wedge E3. And I forgot E2, of course. So basically that's it. So I've got E2 wedge E3. Then let's continue. I've got then alpha 1, 2. And again, I need to look at the only ones that do not have 1 and 2. So, okay, 1 and 2. So here, let's look. Here there is 1, not okay. Here there is 1 and 2, so that's not okay at all. Here there is 2, not okay. So that's this one that is going to be okay. So that's alpha 1, 2, beta tilde 3, 0. And then that's going to be E1, E2, wedge, E3, E0. Now, please bear in mind that what I'm actually caring about here, I mean, the reason why I look for this is because, just in case it's not clear, E0 wedge E0 is equal to 0. E1 wedge E1 is equal to E2 wedge E2 is equal to E3 wedge E3, which is equal to 0. So that's why the only ones that are going to be non-zero are the ones that basically do not appear in the ones I'm taking there. So then plus alpha 2, 3, and then so 2, 3. So then we need to have something that is neither 2 nor 3. So that's going to be 0 and 1. So that's here. So beta tilde 0, 1. But then that's E2, E3, wedge, E0, E1. And then plus the last one is alpha 3, 0. And alpha 3, 0, I want something else, so that would be 1, 2. And so that's beta tilde 1, 2. And that's E3, E0. And then wedge E1, E2. So the next step, and that's kind of a complicated one, is that I need to essentially try to apply permutation so that all of these guys are going to look like this one. So in the order 0, 1, 2, 3. And you need to remember that each time you permute two of these guys, you're going to get a minus sign. And that's what we need to actually count. So here, what I can say is I can do a first swap between E0 and E3. So basically that's the first step, and that's giving us a minus sign. Then I can do between E3 and E0 and E2. So that's the first step, and that's a minus sign. And then I need to do the last one, which is going to be between E0 and E1 to actually get things in the right order. Okay, so that's the first step. So I'm going to actually get out of it a minus sign. Okay, because I've got minus times minus times minus again. Okay, likewise here, let's try to do it. So what I can do is I can basically swap. How do I do that? Yes, so I swap E0 with E2. So E0 with E2, that's the first step, and that's going to give me a minus sign. And then I actually swap E1, so that's step 2, E1 with E3, and basically I'm done. So here this is minus times minus, and that's actually a plus. So that's fine. I mean, that's fine. That's what it is. And then here, basically I can swap. So here E0 with E3, and I do basically the opposite. Okay, so here I was trying to drag the E0 leftwards by always kind of swapping, etc. But here I'm actually dragging E3 rightwards. so left word here, right word here. So the first step here is to swap E0 with E3. Then I'm going to swap E3 with E1, so that's the second step. And then I'm going to swap E3 with E2 as a third step. Okay, so consequently, what we have is this particular expression. So we've got alpha 0, 1, beta tilde 2, 3. Then I've got minus alpha 1, 2, beta tilde 3, 0. Then here I've got plus alpha 2, 3, beta tilde 0, 1. And then I've got minus alpha 3, 0, beta tilde 1, 2. Okay, so that's the expression I have. And this is factorize E0, E1, E2, E3. So the next step here is to basically evaluate this particular thing. And here the way we are going to do it is as follows. We need to evaluate f of alpha beta. So that's the first step here that we've done. And then we need to basically identify that to this quantity. So first of all, we need to evaluate f of alpha beta. And what I'm going to use here is a bilinear property of f of alpha beta. And this bilinear property is as follows. So I'm going to have alpha 0, alpha 0, 1, and then basically we need to take all possible, let me think about it. Yes. So then I need to look at all possible pairs. So here I'm going to have alpha 0, 1, and then beta 0, 1, f of E0, E1, E0, E1. And then basically I've got all these possible kind of sums. So plus, so it's going to be a bit tedious to actually write it all, but let's do it. So here then I've got, well, no, I've got 4 of them, right? So I'm just going to write it for alpha 0, 1, and then we are going to try to find out the matrix here. So alpha 0, 1 here, and then beta 1, 2, and then f of E0, E1, and then E1, E2, and then plus alpha 0, 1, and then beta 2, 3, and then f of E0, E1, and then E2, E3. And then plus alpha 0, 1, and then beta beta 3, 0, and then that's f of E0, E1, and then E3, E0. Okay, so essentially that's what we have for alpha 0, 1, and basically I will need to repeat the same thing for alpha 1, 2, alpha 1, 2, alpha 2, 3, etc., multiplied by every term like this. Now, what I'm going to determine here is what is going to be E0, like basically something like this. So if I have a function of the form f, and then I'm going to say, so alpha, so I'm going to use, well, mu and nu actually. So here I've got E mu, E nu, and then E gamma, E delta, and then we can try to evaluate what that is. Okay, so what it is going to be is essentially we are going to get, okay, so this thing is going to be by definition the determinant of the matrix, which is going to be as follows. That's the inner product of E mu 1 with E mu2. Then, so here that's again how I've defined it. I'm just trying to think again. It doesn't matter. Like as long as this is written like this, it kind of doesn't matter much. But I really want to get things right in terms of the notation. So actually, let's. Sorry, I'm just trying to get it right notation-wise. So here I'm going to say mu1, and here mu2, and here this is nu1, and then nu2. Okay, so the mu correspond to the first entry in the slot here, and then here the nu correspond to the second entry. So let's see why I actually denote it this way is because here I've got e mu1, e nu1. Okay, then I'm going to get e mu1, e nu2, and then here I'm getting e mu2, e nu1, and then e mu2, e nu1, nu2. Okay, so we want to evaluate the determinant of this, and so what we are going to say is the following. This is still the determinant, and now we need to find out various things. So mu1, if mu1, where eta mu1 nu1 corresponds to these particular entries. So this is, sorry, correspond to a matrix with this as a diagonal and zeros anywhere else. So here this is eta mu1 nu1, here this is eta mu1 then nu2, and here eta mu2 nu1, and here eta mu2 nu2. Okay, and then the determinant is going, it's a 2 by 2 matrix, is going to be eta mu1 nu1, eta mu2 nu2 minus eta mu1 nu2 times eta mu2 nu1. Okay, so one of the consequences of this is that e0 e1 e0 e1 is equal to, and let's do it. So that's actually equal to e0 0 times eta e11, and then minus eta e01, and then eta 10. Okay, so this thing is 0 because these are not diagonal elements, and this thing is actually equal to -1. Okay, then let's look at, so in principle that should be -1, but let's look at other ones. So here we've got e0 e1 and e1 e2. So we've got f of e0 e1 and then e1 e2, and that's going to be equal to e0 1, so eta 0 1 eta 1 2 minus eta 0 2 eta 1 1. Okay, so basically that gives you 0. And in fact, what you can see is that the only ones that are going to be non-zero, and actually I could have guessed, are the ones where you actually need to have like the same identical ones. Otherwise, you're going to get a cross thing here that gives you an eta that is non-diagonal, and that doesn't give you 0. That gives you 0. So the bottom line here is that the only non-zero ones are this one, and then basically, yes, and so basically the other one is going to be, in the case of alpha 1 2, well, this is going to be, here this is 0 1, so that's going to be alpha 1 2 is going to be associated to e1 e2, and then e1 e2, so that's going to be eta 1 1 eta 2 2, and then minus eta 1 2 eta 2 1. So this is equal to -1 times -1, and that's equal to +1. And finally, you have f of e to e3. So e2, e3, e2, e3. That's going to be equal to essentially the same thing because they are the same nature. So that's going to be +1 again. And the last one would be f of e3, e0, e3, e0. And this is going to be equal to, so eta 3, 3, eta 0, 0 minus eta 3, 0, eta 0, 3, and that's equal to -1. Okay, so that's what we have. So let's put everything together here. So I'm going to put the plus there, and then I'm directly going to write what we have here. So again, essentially you've got tons of terms to write, but all of the terms that are going to contain essentially basically different terms here. So basically the forms are different in both entries, then, or at least are not a multiple of each other, then you're not going to get something that is non-zero. So that's kind of the bottom line. So here what we get is essentially for alpha wedge beta, we are going by that definition, okay, we are going to get the following. So alpha 0, 1, and then where am I? Alpha 0, 1, so minus alpha 0, 1, beta 0, 1, and then we are going to get plus alpha 1, 2, beta 1, 2, then plus alpha 2, 3, beta 2, 3, and finally minus alpha 3, 0, beta 3, 0, and then that factorizes E0, E1, E2, E3. Okay, and so I will erase here, and we are just going to continue then the reasoning there. Okay, so here what we need to have this equal to that. Okay, so we need to have all of that terms being equal to that for any alpha. So the bottom line is that we are going to get that beta tilde 2, 3 is equal to minus beta 0, 1. Then we have that minus beta tilde 3, 0 is equal to beta 1, 2. Then we have beta tilde 0, 1 is going to be equal to, so that's beta tilde 0, 1, where am I? Here is alpha 2, 3 is equal to beta 2, 3. And then finally the last one. So we are looking at this minus beta tilde 1, 2 is equal to minus beta 3, 0. Okay, so then what we need to do is look at all the possible cases like we did here. So let's have a look at beta. So the first case, that would be beta is equal to E1, so E0, E1. So it means that beta 0, 1 is equal to that, and that leads to star beta is equal to star E0, E1, and that's equal to minus beta, that's equal to minus E2, E3. Okay, because that's a term in front of E2, E3. Okay, likewise, if we've got beta is equal to E1, E2, then star beta, which is equal to star E1, E2. So here you've got that beta 1, 2 is equal to 1, and that corresponds to minus what is in front of 3, 0. So that's minus E3, E0. Then beta is equal to E2, E3. So that's going to be star beta is equal to star E2, E3. And that's equal again, so beta E2, E3. So we've got beta 2, 3, which is equal to 1, and beta tilde 0, 1. So that's E0, E1 is equal to plus 1 as well. And then finally, beta is equal to E3, E0, and that leads to beta is equal to star E3, E0, and that's equal to, so again, 3, 0 is equal to that, and that's actually E1, E2. Okay, so that's the second set we have. The second set of possibilities that we are given. Okay, and that's for the case k is equal to 3. K is equal to 2, sorry. So it was a little bit laborious, and the reason why is because there is this kind of matrix stuff that we need to look at, and we need to have smart ways to essentially see what terms are going to be 0. And I simply, at some point, just didn't see that all of the terms, essentially with different mu's and nu's in the different pairs here, if you've got different pairs here, you're not going to get anything, okay? So that's kind of the idea. And that's why it took a little bit of time, but then basically the point is that it's always that you compare that to that, so that you can make an identification between beta tilde, so the components of the Hodge dual, with respect to then the component of the initial form, or k form or k vector you're looking at. Okay, so basically that's it for this one. And in the next video, we are going to look at the case k is equal to 3.